So now that we've done the main rigid body destruction sim for this creature bursting through the ground, this is looking pretty cool, but we need to fill this out with a whole bunch of smaller scale debris pieces. So I'm going to start by building this debris geometry object to work in, and then we'll dive inside there. And the first step is to build some instance geometry that we'll use for these debris pieces, and we can start with our fractured geometry. So what we're going to do is just grab a few of these fractured pieces, and those will be useful for our debris instances. So let's point this object merge to fracturing and out fracture. And right now this is RBD packed into the proxies versus render geometry and constraints. So let's do an RBD unpack on this. So now we have access to the render geometry directly, and to get a better view of this geometry, we can start by exploding that a bit with the exploded view. And now I'm going to use a couple size filters to trim this down to the size of pieces that I want to use for the debris chunks. Now ultimately, once we select the pieces that we want to use, we're going to make them all the same size before we start instancing them. But the size filters that I use are going to reflect the amount of resolution that I want included on these debris pieces. So for example, some of these larger pieces might be a bit more high res than necessary when they're shrunken down to debris size. So perhaps we could start by splitting out the larger ones that we don't want to include. Let's take a look at our geometry spreadsheet to see what the range of sizes look like. And thankfully we already have this area attribute computed on the prims. So if we sort by that area attribute, it ranges from almost 0 all the way up through 56. So in this initial split, I'll just say area is greater than 1. And if we compare the number of primitives that this is isolating, it looks like that's splitting apart about half of our primitives here. So let's drop a null on the other side to see what the remainder look like. So these are all pretty small pieces that are left over. And right now I feel like this is perhaps removing too many of those larger pieces. So let's raise this area cutoff. I'll try turning that up to a value of 5. Actually, 3 looks pretty good. I'll go with that. I'll call this split large pieces. And then on the second output here, where the smaller pieces are left over, let's do another split. And on this one, we're going to remove the very tiny pieces. So I'll call this split tiny pieces. In the group, I'll say area is less than 0.2. So right now that's eliminating all of these very small ones, and we can start raising this area cutoff if we want to eliminate more of these pieces. Try 0.5. This looks like it's deleting a good portion of tiny pieces there. So I will once again add a null to the second output of the split here. And this is what's left over. We have those kind of in-between sized pieces, and they're generally pretty interesting shapes. So this is looking pretty good. And for the debris, we might not want to include these pieces that are on the exterior of the geometry because they have one very flat face like that. And we already calculated this inside only attribute, so we can use that to delete anything that exists on the exterior of the surface. So let's blast away those. And that group, I'm going to set this equal to inside only equals 0. So if you display that, any pieces that landed on the exterior of the terrain are now deleted. And we can go ahead and just select a subset of these. So let's perhaps try using just 10 different shapes for our debris instances. So I'll drop in a blast, and in the group I'll say 0 through 10, which will actually give us 11 pieces because the value of 0 counts, and that's fine. We'll flip this to delete non-selected, display that, and this gives us a random selection of pieces here. So these are looking like pretty decent, interesting shapes. If you want to get a different random selection of these, one way that you could do that is by sorting your input just before this blast where we're selecting a handful of pieces. I'll rename this blast to select a few pieces. And then just before that, I'll add a sort. And under the primitive sort, we'll set this to random. And then you can play around with the seed value on the sort until you get a selection of pieces that looks pretty good for instancing. And I think this is looking pretty good so far. We'll get a better look at this in a minute after we center everything on the origin and make them all the same size. So to normalize all of these debris pieces, we can use the match size SOP. So let's drop in a for each primitive, or for each named primitive, either should work. In this case, I'll just do for each primitive, drop that down, and connect that to our blast SOP that's selecting a few pieces. And then inside this loop, let's drop the match size. So if we display the for each begin, you can see this is isolating one of our pieces here. And on this match size, this will default to moving that piece to the origin, and it's not going to change the size of it at all. So right now, if we display the end of our for each loop, you can see that all the pieces are moved to the origin here, but their sizes aren't really normalized yet. And this is hard to see at this point because they're all on top of each other. And in this case, because everything's been centered at the origin, we can't use the exploded view because they all share the same centroid. If you drop in an exploded view and raise the uniform scale, you can see these pieces are just staying in place because all their center points are all the same. So in this case, I like to use a point jitter instead. So if you display that, you can see that's spreading out the pieces, and we can raise the scale to spread those out a bit more. And this allows us to get a better look at how the pieces are all lining up to each other. And the sizes of these pieces actually look pretty close to each other, so they're not super far off in terms of being normalized, but we can make this a bit better. On this match size here, we can turn on the scale to fit, and this is going to fit all of these pieces within a 1 unit sized box. But you can see this is kind of distorting them as well. It's ruining the shapes a bit and kind of squaring them off to really fit inside this bounding box. So instead of forcing all of the different axes to fit nicely inside this 1 unit box size, we can turn on uniform scale here. So this will uniformly scale the pieces so that they fit within the box, but it won't force it to fit that 1 unit on every dimension when we use the uniform scale here. And now we have all of these instance pieces that are all the same size and they're interesting shapes, and these will work pretty well for our debris sim. It's also good practice to give these instance pieces a clean name attribute. So let's drop in a wrangle, and we currently have a name attribute on the points of all of these pieces. So I'll connect the for each to our wrangle here. The vex will set a new string name attribute equal to debris underscore, and then just add the point number. So we'll say plus I to A to convert the point number to a string representation. Pass in the point number pt num. And now if we check the spreadsheet, now we have nice names for all of our pieces. You can see they're now numbered debris 0 through 10. However, it looks like our name prim no longer matches, so I suppose it's also a good idea to set the primitive name as well. So I'll do the same thing that we did before at the fracture setup. So we'll do an attribute promote from point to primitive, select the name attribute. We don't want to delete the original, and we'll change the new name to name underscore prim, which already exists, but that's fine. Set that name underscore prim. And if we check the spreadsheet, you can see that now the point names are once again matching our primitive names as well. So that keeps things nice and clean like that. And now we can cache these to disk. So ultimately, we're going to have a ton of these little debris pieces added to our destruction sim. We could have thousands and thousands and thousands of these things. So if those were all raw geometry that were getting cached out and rendered, that could get very heavy, and we don't want to do that. We want to leverage some packed object optimization. So we're going to use packed disk instances for this. So if you remember what we did for the rocks, we isolated one piece on every frame. So I'll drop in a blast, set the blast group equal to $F, set that to delete non-selected and display that. And because we only have 11 pieces and we're on frame 49 right now, we're not going to see anything here. So if we go back to a frame less than 12, you can see now we're getting one of these debris pieces per frame, and we can cache these out with our file cache. So I'll drop in this new file cache here. Now for the frame range, we're going to start this at 0 and then reference the number of points in our instances to set the end frame. So just before this blast stop that's isolating pieces, which I'll rename for clarity here, we can add in another null that we can use to reference the overall number of instance pieces there. I'll call this null all instances. And then in this file cache here, we'll use an endpoints reference for the end frame. So say endpoints and point that to ... / all instances. And currently, this is going up to instance number 11. But even though we have 11 instances here, we only have instances available on frames 0 through 10, since numbering starts at 0. So we have to subtract 1 from our endpoints here. So this will cache frames 0 through 10. And I'll point this to job geo destruction. And we'll make a new instances debris directory. And when saving out each of these instances, we don't want to use a frame number with padding, because this will be more of a pain to deal with if we use a file merge to bring those all back in. So I'm just going to use $F instead of $F2 or F3 or so on. So $F.bgeo and accept that, and then save these instances to disk. So that was quite quick, just took several seconds. I'll rename that cache instances, and then we can merge those back together before instancing them onto some debris source points. So to bring them all back in, I'm going to use a file merge, and I'll point this file merge to the same instances debris path that we just cached out. So that's instances debris version 2 $F.bgeo, but you can see that the file merge is using a merge variable called slice to merge in all of those geometries that we've cached out. So instead of $F, we're going to change that to $slice to use that merge variable. And the range, we can just copy a reference to this file cache here. So I'll right click that range there, copy that parameter, and on the file merge, let's paste in a relative reference. So if you display that file merge, this is bringing in all of those debris pieces that we've cached out, and right now they're being brought in as normal packed objects, but we want to make these packed disk instances. So under load, let's select packed disk primitive, and I'll set the display as to full geometry. So now it doesn't look any different in the viewport, but now if you middle mouse on the file merge, you can see these are packed disk instances that are just referring to that geometry on disk. So essentially when we have thousands and thousands of these debris pieces and we cache these packed disk instances out to disk, then we don't actually cache out all of the geometry. It's really just caching out the instancing information that's pointing to this geometry that's existing on disk. So for our purposes and the way that we'll be setting up our debris sim and caching it out, this is going to be very helpful, and this is going to offer a much cleaner and more efficient workflow than if we were just using normal packed geometry. So we're all done setting up these instances, so I'll just wrap up by dropping in a null after the file merge. I'll call this debris instances, and we'll select the whole thing, drop a netbox around that to keep everything nice and clean, and then we can move on to setting up the actual debris sourcing and simulation.